Welcome to the wave mechanical model of the atom, Chapter 11, Part 4. Unfortunately, probably not going to get to the actual wave mechanical model of the atom at this point. I'm mostly just going to build on the idea that if light can behave as both a wave and a particle, can anything else behave as both? This question was first posed by a Frenchman. I believe he was a prince. De Broglie is how we say it in America, although I have been told it should be pronounced like de Broglie. However, the point being is he ran this equation of his own device and discovered that yes, matter can have properties of waves. Fortunately for you guys, we're in Gen Chem, so we don't have to do anything with this equation. But it does allow us to look more closely at Young's double slit experiment. Before we can start talking about the double slit experiment, we need to start talking a little bit about what happens if there was only a single slit. For example, if I were to take a medium-sized particle, say bullets, and fire them at a wall that had a hole or a slit in the wall, then what's going to happen is each one of the bullets that actually makes it through this hole is going to land right here on the wall. And if I turn the wall so you could look at it, you know, this is like I put the wall flat here on the ground, tipped it over if you will, then see this pattern looks like this. You have all the bullets in this nice straight line. And if we look at a single slit pattern with a wave, for instance, let's take a look at light. Light, we know light's a wave, right? Well, okay, it's a wave and a particle, but let's look at light as a wave. This light will come straight through this barrier and produce a very bright spot here in the center, and as you move away from the center, the light becomes more and more dim. And another good way to think of this is think of this not as light, but say of water waves. If water waves hit this barrier, but we're allowed to get through the center, they would form this ripple pattern, and you'd end up with, if you had a detector screen back here, the brightest spot, the most intense part of the wave striking right here in the middle. Now, let's go to the double slit experiment. This time, again, we're going to use bullets, a classical particle, something that behaves like we fully expect it to in the world we live in. So now I have two places in this wall that the bullets can pass through, and sure enough, they all land pretty much where you expected, showing the pattern if we were to put the wall flat, but a pattern. Just as we would expect, all along the bullets that cannot penetrate the wall, because there's this big old barrier, they don't make a pattern back here. Now light does something a little bit more interesting, and I see an error here. This should be double slit. I apologize for that. Double slit. Okay, so light does something, and so does water. As a matter of fact, if you think of water waves, much more interesting in a double slit. See, if you take this light or these waves and they're allowed to pass through two different spots, they make this amazing interference pattern. It's both constructive and destructive interference, where you get these patterns all across the back of these very bright spots of greater intensity, and patterns with dimmer spots of lower intensity where the waves had destructive interference. Quantum means small. That seems to be an error that a lot of students have, but a quantum particle is a very small particle, small like an electron. Now, if you take an electron and you take an electron gun and you fire the electrons at basically, let's think of it as a wall with a single slit in it, they all hit right here, showing the same pattern as the bullet did. Awesome, no problems with that. But if we take a double slit with a quantum particle, do you think we're going to get the exact same results as we had with the bullets? We don't. We don't get this at all. Nope. This is not what happens. We get an interference pattern. What? I know, right? This doesn't make any sense at all. It didn't make any sense at all, so scientists were desperately trying to understand, well, the thought was maybe those electrons, since they're not bullets after all, they're much smaller, they were interfering with each other. So this was a picture of a double slit experiment taken of 100 electrons shot one at a time. Now we have a picture of 3,000 electrons, each one shot one at a time. I don't know about you, but I'm starting to see an interference pattern. Can you see where the darker bands and where there's bands of not so many electrons? Maybe not yet. Can you see the bands now if we shoot 20,000 electrons one at a time? 700,000 electrons shot one at a time. You can now clearly see an interference pattern. But how can that be? How can you have an interference pattern with electrons when they were shot one at a time? The only logical conclusion was the idea of superposition. And one of the ideas with the superposition is that the particles, in this case the electron, must have wave-like behavior. It has to. That is the only way to explain this. And that it goes through the slit at the exact same time, and it interferes with itself. And that is the only explanation for how a particle shot one at a time could possibly behave like a wave. And it's this idea of superposition, where something can be in more than one place at the exact same time. And if that idea hasn't blown your mind already, things get even stranger. You see, this whole idea of a particle that is acting like a wave and can belong in more than one place at exactly the same time is so against everything we could possibly think of. It's so like not even part of our own world that the next idea scientists had was, okay, wait, what if we record the behavior so we can see exactly which slit this electron's going through, because it can't possibly go through both at once. So when we recorded the behavior, we got a different result. The act of recording the behavior changed, recording what it did changed the behavior. It now started acting like a particle. It can't possibly act like a particle just because you record it. That's stupid, right? So maybe the problem was with that recording equipment, the detectors, maybe something was interfering. So scientists left the recorders off, left the detectors in place, but turned the recording off. And the electron went back to behaving like a wave. And things still get stranger because, okay, maybe it's not the recorder, maybe it's not the detector, maybe it's the tape in the recorder. So the tape in the recorder was removed and everything else was turned on, and they still went back to acting as if they were a wave. The result: the simple act of recording collapsed the superposition into one reality. You cannot record or measure two realities at exactly the same time. Only one reality can be measured at one time. The results of the double slit experiment are fairly mind-blowing, and that's why Schrodinger's cat came to be. Schrodinger's cat is a thought experiment meant to help people understand the idea of superposition. And so I'll be uploading a couple more videos that I'd like you to watch regarding superposition, so you can have a better idea about Schrodinger's cat. But what you really need to know is your conclusion. Energy is really a form of matter, and all matter, like an electron, shows the same type of properties as energy, such as light. All matter, all of it, has both particle and wave properties. Superposition at its best. Very large things like baseballs and have extremely small wavelengths, and they act mostly like matter. Well, that one cracks me up. Intermediately sized things like an electron, I know, I have a trouble, that just blows my mind anyway, show both properties of waves and particles. And very small things like a photon have larger wavelengths and they act mostly like waves. Up next, what does all of this mean for where the electron really lives?